The superposition principle says basically two things, that two waves or multiple waves can occupy the same space at the same time. And it says that the net displacement of the medium is equal to the sum of the two individual, we'll leave it to the two waves for right now, the individual displacements that each wave would cause. So let's go down here to constructive interference. Suppose in a medium, let that be a string, I have a wave pulse that looks like this, and it's moving that way, and I have another wave pulse that looks like this, and it's moving this way. Well, what's it going to look like when the two waves both get to right there? Well, you would, because the wave displacements are both, in this case, positive, they're both above the equilibrium line, they will add together. The superposition principle says that the displacement is the sum of the displacements, and these would both be positive. And so this wave would make the medium move to here. This wave would make it move this much higher, so like up to here. So what you would have when both waves were there at the same time would be a displacement that looked like that. And because the displacement's bigger than the two waves were individually, it's called constructive interference. So you can probably guess what destructive interference will look like. If I have, there's my medium, and if I had this wave moving this way, and I had this wave with a negative displacement moving that way, well, what's it going to look like when they get to the same point? Well, this particle would move to here if the light blue wave got there by itself. It would move to here if the green wave got there, and this is a negative displacement and this is a positive displacement, so they add, but they're opposite signs, so it's kind of like a subtraction. And so the resultant wave would be here, and that would, well, sorry, this is destructive, not total. Well, what is total? Sorry for the error here. What is total destructive interference? Well, it would be where the waves were on the opposite sides and had the same amplitude, but opposite, so they would completely cancel. So if I had a wave that looked like this, moving this way, a wave pulse, imagine plucking a string, and I had a wave that looked exactly the same, but on the, oops, that's the same color, isn't it? It did look exactly the same. Same size, but on the other side, then when they get to the same point, this particle would move this high if the blue wave came. It would move this low if the green one comes. And so the two energies, or the displacements cancel each other out, and you get total destructive interference, a zero displacement. Okay, standing waves. You've seen standing waves happen. If you pluck a guitar string, it sets up a standing wave. I'm going to go to this YouTube video quickly. We're not going to watch very much of it, but this guy's going to make a standing wave. Ooh.
So then a standing wave is where you pick a frequency that matches the length of the string in such a way that the waves created from my side of the string and bouncing off of Parker's coincide with each other and reinforce each other to create a standing wave pattern. The lowest frequency standing wave pattern is this one. It's called mode, M-O-D-E 1, or the first harmonic, or in other words, also called the fundamental mode. It's the lowest frequency mode that you can get in a transverse standing wave. If I double the frequency of that mode, I get the second harmonic, or second mode, and sometimes called the first overtone.
Okay, that's all we really needed to watch. So that standing wave pattern, when you shook it in such a way that that slinky vibrated like this, up and down as one full unit, that was the fundamental frequency of that slinky, it's also called the first harmonic. We call these points where there is no displacement, we call those nodes. And this point where we have maximum displacement, we call either a loop or an antinode. When he shook it faster, he got the second harmonic, same slinky, but it was vibrating with this pattern. Notice in this case, the wavelength of a wave is equal to the length of that string. And in this case, we had 3 nodes, and we have 2 antinodes. This is an antinode here, and this is another antinode here, so 2 antinodes. And that is the second harmonic. And you can count loops or count antinodes to know what harmonic it is. Antinodes happen when you have alternating constructive and destructive interference. Nodes happen where you constantly have destructive interference of the incident wave and the reflected wave. This is another picture as the harmonics get more and more complex. This is the first harmonic, just like we drew, with the whole string vibrating as a unit. The string length is 1/2 of a wavelength. And the second harmonic, just like we drew, the string length is equal to a wavelength. And all the way down here to the 6th harmonic, you can tell it's the 6th by counting the antinodes. There's 1, 2, 3, 4, 5, 6. So 6 loops or 6 antinodes, and you have the 6th harmonic. To find the frequency of the first harmonic, also called the fundamental frequency, you can use this formula, but you need to know the velocity and the velocity and the wavelength. So the frequency of the fundamental frequency, or the frequency of the first harmonic, would be equal to the wave speed in that medium, so how fast does the wave move on that string, divided by the wavelength. Fundamental frequency on a wave on a 2-meter long rope. Okay, so if it's vibrating like this and the rope is 2 meters long, then the actual wavelength would be 4 meters, because in the fundamental frequency, it vibrates, the whole string length is 1/2 of a wavelength. Find the fundamental frequency, 2-meter long rope traveling at 2 meters per second. So the frequency would be 2 meters per second divided by 4 meters, so it would be 0.5 hertz. This is that longitudinal wave.